You could get fined for forgetting to buckle up in a 2-ton sedan. Yet every morning, we let 40 children sit freely inside a nearly 5-ton metal giant speeding down the highway. No seatbelts, no familiar click. Through the lens of modern fear, it looks like collective negligence. But through the lens of physics, it's a cold, precise calculation. A school bus isn't missing safety equipment. It is the safety equipment. And the paradox is, this sometimes the best protection isn't strapping a body down, but designing an entire environment where collisions are neutralized before they can become disasters. To understand this, we have to return to the most basic principles of mechanics, where mass, energy, and space quietly decide human outcomes. In classical physics, kinetic energy is described by a familiar equation: E equals 1 divided by 2 square millivolts. Double the speed and the energy quadruples. But mass plays an equally critical role. A sedan typically weighs around 502 kilograms. A large school bus can weigh 7 to 10 times that amount. When two vehicles collide, what matters isn't just speed, but momentum, the product of mass and velocity. In a crash between a bus and a car, the smaller vehicle absorbs most of the sudden change in speed. It stops almost instantly, like a handbrake slammed in a split second. The bus, meanwhile, slows down, but is rarely thrown violently or severely deformed. Imagine a mouse running into the leg of an elephant. The mouse stops. The elephant pauses for a moment, then keeps walking, not because the elephant is emotionally stronger, but because its mass creates enormous inertia. That inertia is the bus's first layer of armor. Decades of U.S. statistics show that the fatality rate per mile traveled on school buses is significantly lower than in private cars. Not because drivers are flawless, but because the system is built to exploit the physical advantage of large mass. In a battle between elephant and mouse, the elephant is rarely the one critically injured. But mass is only the first defensive line. The second lies in how the interior space is organized. Picture an egg carton. You can shake it gently without breaking every egg, because each one sits in its own compartment, surrounded by walls that absorb force and limit movement. School bus seating follows a similar philosophy, a concept known as compartmentalization. Bus seats aren't traditional seats. Beneath the vinyl covering is thick polyurethane foam, a closed-cell polymer structure. Under impact, the tiny air pockets compress, absorbing part of the collision energy through elastic and semi-elastic deformation. Mechanical energy doesn't vanish. It transforms into heat and material deformation. The spacing between seats is intentionally narrow. Seatbacks are tall and reinforced with steel frames. In a frontal crash, the most common scenario, students don't fly freely through a large cabin. Their bodies meet the padded seat in front of them, like eggs cushioned by their carton walls. Limited space becomes a passive seatbelt. The key here is force distribution. Instead of concentrating force into a narrow strap across the chest, impact forces spread across the back and head over a larger surface area through thick padding. In many urban speed collisions, this system significantly reduces the risk of severe injury. So that hard and ugly seat is actually an energy barrier. It doesn't try to hold you still. It controls your trajectory within a pre-calculated space. There's another often overlooked factor: height. Look at the cross-section of a school bus. The floor sits much higher off the ground than in a car. This isn't just for better visibility. It creates a crash zone beneath the passenger's feet. In most bus car collisions, the lower front end of a car strikes the bus's undercarriage and wheels.
What
Impact
happened?
forces travel into the suspension,
cabin held up.
steel frame, and structural
everyone
components
okay?
below, rather than directly into the passenger cabin. In other words, a bus doesn't fight collisions head-on. It stands above them. The steel frame architecture and high ground clearance create a physical buffer layer between danger and the children inside. This is an architectural strategy. Instead of reinforcing each passenger with belts and airbags, the entire vehicle becomes a moving fortress.
Move
The
to the
passenger
front.
compartment becomes
Everybody
a core
out
zone,
now.
where outside forces must pass through multiple structural layers before reaching anyone inside. Yet every design must face a final question: what happens when an accident doesn't end with impact, but turns into a crisis? Imagine a rare but serious scenario. A bus catches fire or submerges in water. Time is no longer measured in minutes, but seconds. In collective panic, every complicated action becomes a barrier. 3-point seatbelts, while effective in cars,
Keep moving.
require locating
Let's
the
go.
latch, pressing a button, and freeing oneself under stress. For adults, it's reflexive. For small children, especially when shocked, it can become an obstacle. That's why the absence of
closing fast.
seatbelts on
Wait, help
large
me.
buses reflects a different
slide.
philosophy, minimizing escape complexity. When necessary, students can simply stand up and move. No cutting straps, no unlocking mechanisms. Rear exits and emergency windows are positioned to maximize the flow of people. This is the paradox of release. While we often assume that holding tighter always means safer, in certain contexts, the ability to escape quickly is what determines survival. Safety design doesn't just consider collision probability, it also accounts for fire, flooding, rollovers, and the reaction speed of real humans. Not ideal ones. School buses aren't safe because they lack seatbelts. They're safe because the entire system matters. Seat structure, floor height, and evacuation strategy is designed as an ecosystem of forces. In this case, safety doesn't come from strapping each individual into place. It comes from predicting every possible impact and dispersing its energy through space, material, and time. Every layer of steel, every block of foam, every seat distance answers the same question: where will the force go? And once you understand that, the paradox disappears. What looks like a missing feature becomes a peak example of systems thinking. Sometimes, the best way to protect an egg isn't tying it down. It's designing a box where it simply cannot break.